Imeandikwa MD on the side, kama nataka display kadogo ama inaweza kuwa ni FTC. Kama haiko hapo kando ya raka, hakuna haiko anywhere in the server room. It's nothing. Inakaa box tatu zimeunganishwa pamoja. 3 compartments. Yeah. Unaona? Angalia kwa haraka. Hii iko na server. Chini kabisa iko na nini?
TikToks, data, whatever you are.
MD ndio hiyo sasa.
TikTok.
Inakiwa.
Festus.
Haya, hiyo MD iko na display.
TikTok Festus. Mute. Now, welcome. Today we are now going to look at the antennas. I'm going to start straight away, so you can tell me whether you can see my documents before I start. Is everyone able to see it? So we are going to look at antennas and radiating systems. The curriculum or the course outline requires us to just give an introduction, and therefore I'm not going to be very exhaustive about the antennas that there are, but we know that there are very many types of antennas. Some of these will be covering in the 5th year for those of us who will be taking the microwave options. So what we are going to do is just to introduce how the radiating systems come and when we need the radiation and when we must suppress radiation. So the important concepts that entail is that often we desire to direct electromagnetic energy in a specified direction efficiently. This would happen especially, say, for example, the new 5G new radio, because of the, you want to target the radiation to a particular device, okay? And that's the beauty of the 5G environment now, where we shall be using very thin beams by using multiple arrays of antennas with a lot of beam forming so that you can send it in a given direction. This will allow you to use less power in transmission and you waste less, so to speak. So therefore, this will require that the charges and the currents that establish the EM fields have prescribed special distributions. We recall that when we started this course in the last semester, we say that the eventual or the actual source of electromagnetic waves is the charges and the currents that are moving in space in a given distribution. So structures and are designed to optimize these distributions will be called antennas. So EM energy will be localized in space without the antenna, and this renders the long-range wireless communication practically impossible. So in a way, the antenna can be viewed as a system matching the feed structures to the free space. By feed structures, we are saying the transmission lines that are getting the signal from the signal generators to the antenna system, and the antenna system is therefore sitting between the system generating the signal and the feeding, and as well as the medium into which the waves are to be launched. So the important parameters to consider in an antenna design would include the spatial field distribution or the radiation pattern of that antenna. 2, the maximum radiation in a given direction, and this is usually referred to as the directivity of the antenna. It's more like when you have a spotlight, if you don't have the reflector or the parabolic reflector behind the light emitting diode or even the bulb, the light will be spread in all directions. But then if you want to point it in a given direction, of course, you use the reflector, and the reflector collimates all these rays to go in a given direction, and therefore for you to see anything will be directing the spotlight in the direction that you desire. So the directivity of the antenna is usually defined in terms of the maximum radiation in that specified direction. So the antenna impedance, the impedance is usually important because, like we have said, the antenna is going to act as a matching system of impedance matching system between the generators and the free space, and therefore the input impedance is important because we don't want reflections. We want all the power that is being generated by the signal source goes into the antenna without reflections. The radiation resistance is a fictitious kind of resistance that represents the power that is radiated into space. And therefore, we shall see how we'll define what the radiation resistance of an antenna is and why it is important. Then we have what we call the bandwidth. What we shall see is that an antenna will radiate efficiently over a very narrow range of frequencies. Usually, frequencies for which the wavelength is almost of the same order of magnitude as the antenna itself. And therefore, if we change if the signal is broadband, then you might have to use broadband antennas, okay, for this kind of applications. And we shall see how we can try to improve the bandwidth of the antenna. But in many cases, will be narrowband because they are usually resonant antennas, so to speak. So, while application of Maxwell's equations in antenna analysis is theoretically feasible, this is usually not practical because, one, it requires that the space distributions of the current and the charges over the radiating surface be completely specified. Two, this is not often not the case, and in many structures of interest, this would be very, very difficult to determine. So, fortunately, radiating fields of an antenna is relatively insensitive to the slight changes in the distribution of those currents and charges on the radiating surface. And hence, the approximate distributions will often suffice to give us a rough idea of how the antenna would behave when connected or inserted in a system. So, in antenna studies, it is often convenient to start from the potential functions because we saw that before that we can always describe all the magnetic fields and electric field components by just getting only one of the potential, okay, using the Lorentz conditions. So the functions of course that we know and we can recall from last semester are one, the magnetic vector potential A given by the integral of the current distribution over the volume of space of interest, so to speak, and where we have given the definitions of the given variables in this particular equation. And of course, we have the electric scalar potential phi, and also given by the given values there. And this, you recall, is what we are saying that the vector potential and the scalar potential are given in their retarded form, where the retardation is given by the propagation factor exponent of minus jk r, where r is of course the distance of the field point from the source point. So the fields here have been assumed to have a harmonic time dependence, and the V prime is of course the volume that contains the sources of the electromagnetic fields, which are of course the current density and the charge density. So the magnetic and electric field intensities are then obtained from the curl of A. That is, since we have seen that the divergence of B, that is the magnetic flux density, is identically equal to 0, then we can always define B as the curl of a vector. Okay? And that's why we are using that 1 by mu, where we are assuming a linear kind of medium, where now B is related to H as mu H. And the electric field is of course going to be given from the Maxwell's, from the Ampere circuit law, which is the curl of H equal to the time derivative of the electric flux. So A and phi are related through the Lorentz condition, which we say that the divergence of A is the same as the minus of the time derivative of mu epsilon multiplied by phi, where the time derivative, of course, is given by j omega. So J and P and rho are related through the continuity equation, which says that the divergence of J is equal to the time rate of change of the volume charge density, rho. Remember that rho represents free charges, therefore they can move in space. To determine the fields only, J will then need to be specified, and then we can determine A from J. Then we can determine H from the curl of A, and we determine E from the curl of H. And therefore, once we have specified J for a given antenna or radiating system, then we can get all the rest of the field quantities that will be required. So the first approach we look at is what we call the electric dipole. And this is usually an elemental or a very small short wire. So we are going to consider an elemental oscillating electric dipole in the form of an infinitesimally small or filamentary conducting wire of length L that is much smaller than the wavelength at the frequency of interest. And this is isolated in space. So our filamentary current element is given there with a length of L, and it's an open-circuited thin wire, so to speak. By thin, we mean that the radius of that wire is much, much smaller than the signal length, so to speak. Then we are going to look at P, at a point P, which we shall call the field point, and we want to see what would be the electric or the magnetic vector potential generated at P from the current element, because we remember that a current will always generate a magnetic field from Ampere's law. So our elemental current element is chosen to be oriented in the positive z direction or along the z axis, and we are looking at x pointing to the left, to the right, and y is therefore pointing into the board or into the screen, so to speak. Now, the distance from the center of the wire to the field point is given by the vector r. So r is the position vector of the field point from the center of the wire, which we are taking as the origin of the Cartesian coordinate system. So one end of the wire has a vector a vector r prime to the field point, and the bottom has a vector r double prime to the field point. And therefore, we shall try to see how these two are related. So, because the wire is open-circuited, then we can expect that there will be accumulation of charge at the endpoints and accumulation and the negative charges on the other side. But remember, since this one is a time-varying kind of oscillation, therefore one side will be positive and negative, and then at another time, of course, will be changing to negative and positive. So they are oscillating around that wire in that form. In many cases, we shall see that we shall need L to be much smaller than lambda, because then we can assume that the current distribution or the current density over this wire is going to be uniform, that is going to be the same throughout the length of the wire. That's hence the reason why we want to make this assumption. So the wire carries a current I of Z that is uniformly distributed over its length because of that assumption that L is much smaller than lambda. And this is then what we call an electric or a Hertzian dipole. Because of the open circuit on either end of the filamentary wire, large conducting disks or spheres may be attached at the ends to help keep Lz constant throughout the length of the wire. And this will then be called capacitive loading. So we assume that Iz has a harmonic time dependence, and we write that Iz of t is given by I of t equal to I cosine of omega t, which is just the real part of the current phasor multiplied by the time variation given by the exponent of j omega t, and we take the value of the real part, where we are using cosine omega t as the reference function. So the current must vanish at the ends of the wire, and we must then have charge accumulation at this point. From circuit theory, we can always write I of t as the time rate of change of the charge, and this is going to be given by the derivative of the real part of the charge phasor and multiplied by the value of the exponent of j omega t, where the charge phasor is, of course, the distribution of the charge along that wire. So since I of z is equal to I and is constant over L for that, when we assume that short length, then we can write that I is going to be given by j omega q, and therefore tells us q is just the same as I divided by j omega. That is the integral of the time integral of the current. So the electric dipole, then formed by plus or minus q at the ends of the wire, has an electric dipole moment given by P equal to Z cap Q multiplied by N. Remember that the dipole moment P, okay, is of course the charge, one of the charges, usually the positive charge multiplied by the charge separation L. And this can be given as Z cap given by I by J and multiplied by L. And taking I as the total current flowing through the wire, then at P, the magnetic vector potential will be given by a value that A equal to Z cap mu by 4 pi multiplied by the current and multiplied by the length of the dipole and divided by the distance from the dipole at the field point and multiplied by the propagation constant exponent factor exponent of minus j kr, which is what we were calling the retardation effect of the, that is, it takes time for the effects happening at the wire or at the antenna to be felt at the field point at P. So we conclude, therefore, that the magnetic vector potential A, okay, at a field point, a distance r from a z-directed current will also be z-directed. This is very important to keep in mind, that the vector potential A will always be pointed in the direction of the current for generating it at the field point. So the radiation studies, many of the problems have spherical symmetry, and it's therefore often convenient to use a spherical coordinate system. And we have for this system that the unit vectors in the three Cartesian coordinates direction x cap, y cap, and z cap will be given as follows: that x cap is going to be given by the unit radius vector r multiplied by the sine of theta, the cosine of phi, plus the theta cap, that is the in the theta direction cos theta cos phi minus phi cap sine phi. Remember that theta is called the elevation angle and it's measured positive from the positive z axis towards the plane xy. And r is measured from the origin going along the radius of a sphere, while phi is measured from the positive x direction towards the in the xy plane towards the y direction, so to speak. So, and it's called the azimuthal angle around that sphere. So y cap will be given as well by that, and the z cap you can therefore see just going to be given by the r cosine theta minus theta cap sine of theta. So hence, given that A in a spherical coordinate system is going to be given by r ar plus theta cap a theta plus phi cap a phi, where the ar, a theta, and a phi are the r radio, the elevation and the azimuthal components of the vector potential, then we can extract AR, A theta, and A phi from the Cartesian representation of A as follows. That is, the radial component is just going to be the projection of the vector potential along the radius of the sphere, and we get a value of AZ cos theta. That is, if we multiply AX, that is this value, r cap dot that, you can see that this part will remain. Then we'll have that part will have to go to 0 because r, theta, and phi are orthogonal, just as x, y, and z are orthogonal, and therefore those ones will fall out, and we are left with that kind of value remaining at point. And 2, and all the rest will follow. And we see that for this particular kind of vector, that is for a z, that is the azimuthal component, is going to be equal to 0 throughout. So, in other words, we can therefore write that the radial component of A is going to be given by mu divided by 4 pi, multiplied by the current theta, and multiplied by the length of the dipole, divided by the radius or the distance of the field point from the current element, multiplied by the cosine of theta and the sine of minus jkr. And A theta is going to minus jkr. Once we have that, we can say that the reason we have axial symmetry, the reason we have A phi equal to 0 is because of the axial symmetry for the z directed dipole, and therefore means that there will be no variations in the phi directions as well. And that means that d phi is going to be always equal to 0. So in spherical coordinates, we can therefore write that the curl of A is going to be given by 1 over r squared sine theta multiplied by this curl equation, which is represented as the magnitude of, or the norm of a vector that is given in that form, where we have the vectors, and the vector values are of course r cap multiplied by theta cap. R, remember that theta cap is an angle, and when it's measured in radians, it will have no units, and we must have units of length. Therefore, we must multiply by length, and also the phi cap will also be multiplied by length to get the value of that, to get all of them having the values of length for the spatial kind of derivatives. And then, of course, we have those others. If you can recall the Cartesian coordinate system, we had a similar value where we wrote that the curl of A is given by x cap, y cap, and z cap. And then we have ddx, ddz, dy, and ddzz, and then the ax, ar, ay, and az at the bottom. So this is the same kind of thing, but now we are using the spherical coordinate system. And therefore, we obtain the magnetic field intensity as the curl of A and divided by 1 by mu, and therefore we can get this as given as only a phi cap, that is H will be directed around the current element, that is around the wire circumferentially, and therefore we only have the phi directed component of H. And once we do the actual derivatives or the differentiation of these values here, we'll get a value of minus phi cap, the current I multiplied by L divided by 4 pi. The k squared is of course given by that value of the propagation constant, which is twice pi by lambda, and for omega divided by c, we multiply it by the sine of the elevation angle theta, and we have this spatial function where we have 1 by jkr plus 1 over jkr all squared, and multiplied by the propagation factor exponent of minus jk and r. And what we note is that for a z-directed current element, the magnetic field intensity is entirely circumferential, and it's no longer the radial components and the theta components are all going to go to 0. So we have only one component. So this expression here is going to give us a few of the things that we shall see about the radiation, where the radiation comes from. 2, the electric field intensity, of course, is going to be given by 1 over j omega epsilon and multiplied by the curl of H, that is from the Ampere circuit law. And therefore, once we do that, we are going to have E as 1 over j omega R, and then we'll use the curl equation for that value of H. Of course, we are going to do the same thing as we did for the A, only that we change the A values by the H values. And remember that H, or the magnetic field intensity, has only one component, which is H phi. So once we do the differentiations, then we'll see that we'll have a radial component for the electric field, and it will be given by I, the current multiplied by the length over 4 pi times the intrinsic impedance of the medium surrounding the current element multiplied by the propagation constant square and twice cos theta and multiplied by that value plus the other. What you can remember, if you recall your electromagnetics or electrostatics from third year, the twice cos theta was appearing as the dipole, okay? The electric field due to a charge, like an electric dipole that is having a Q and a minus Q. So this you must remember from your electrostatics, and we shall see that this particular component will be called an induction component. And 2, we have an elevation or an E theta component with the similar value with sine theta. And we see that for this particular case, we have only those values appearing there. So, and multiplied by the cosine or the exponent of minus jk r. And what we notice is that we don't have an E phi component, and this is because of the spherical or the circumferential or axiosymmetry we have for our current element. So, we note that even for a simple structure, such as the electric dipole, the field distributions are therefore quite complex. Now, we can analyze these fields by making certain approximations. 1, we have the near field approximation or the near field zone, where the Kr is much, much smaller than 1, and the spatial variation will then be faster than 1 over R. And this region is usually called the Fresnel region, but it's not really called the Fresnel region because the Fresnel region is between, is slightly further from the near field zone. Okay, you could call it the induction zone. What we shall see is that most of the time, if we look at these expressions here, okay, these values here is going to be when Kr is much smaller than unity, this will be the dominant factor. That is the 1 by Kr cubed, because R squared will be small, but R cubed is also going to be much, much smaller. And since it's at the bottom, then this will become very large compared to the rest. And therefore, you can always approximate the ER by that. And the same thing will happen for the E theta for that particular case there. Then we have what we call the far field zone, where Kr is much larger than unity, and the spatial variation is then going to be 1 by R, and this zone is usually referred to as the Fraunhofer zone. The Fresnel zone and the Fraunhofer zone comes from physics, from the two guys who are looking at a diffraction of waves. So when Kr is much smaller than unity, we can therefore approximate the exponent of minus jkr as 1 minus jkr minus 1 by 2 factorial jkr squared plus so forth. That is, we are expanding that in a Maclaurin's series that is about r equal to 0. And therefore, the dominant terms in the magnitude of the field expressions will then be the Kr squared and the 1 over Kr minus 3. And we find that H phi is therefore going to be given by 1 I, okay, the current multiplied by I and divided by 4 pi r squared. Recall that this is now the surface of a sphere, and we are multiplying that one by the sine of the elevation angle. And this is the same as the expression that you obtained when you are looking at current elements of I multiplied by L when you use the Biot-Savart law in electromagnetostatics in the 3rd year course. Now, similarly, ER is going to be given by that expression there, and we can see that this can be expressed in that form, and we get the polarization of the electrical, whatever dipole moment P divided by the volume, or that is 4 pi epsilon r cubed and twice cosine theta, which is again the same form you obtained when you are looking at the electrostatics in the 3rd year. And E theta, of course, is going to be given by the same value, where we are using I by j omega is the Q, that is the, and Q times L, of course, is of course the, that is of course the same dipole moment there, but with a sign. And you obtain this, of course, you really obtain the same expressions when you are studying magnetostatics. And therefore, we can say that these are the same expressions obtained for the static element electric dipole oriented in the z direction. So in the near field, therefore, the fields are quasi-static, that is, they are not the dynamic fields. So the dominant field components in the far field or the Fraunhofer zone will be those that are varying no faster than 1 over r, okay, which is the Sommerfeld radiation condition that we mentioned when we were talking about the magnetic fields and their boundary conditions. And hence, H phi will therefore be approximately given by the first part, and we see that it has a J there, and we have the current multiplied by the length and divided by 4 pi r multiplied by the propagation factor K sine theta multiplied by the exponent of minus j kr. And therefore, if we were to convert that one to the instantaneous value by multiplying that one by the exponent of j omega t and taking the real part, we'll get that it will have a sine omega t minus kr somewhere. And this, you recall from what we've been discussing, is the expression of a propagating wave. And the same thing will be given by E theta. And since H phi and E theta are orthogonal from each other, that is, they are 90 degrees, if we were to divide E theta into H phi, we shall see that we'll get a constant value that will be eta, that just eta alone. Because you can see that that function, that factor there is the same as that factor. The k and that k is the same, that and that is the same, and that is the same. The only difference is the eta. And therefore, we see that the H phi and E theta are related, that is in the far zone, that is very far away from the current element, are in the same relationship as the fields in a TEM wave. Only that here, instead of having a plane, a uniform plane wave, we have a spherical TEM wave instead. So this is what we have said. And we can say that H and E are in spatial quadrature phase. That is, they are at 90 degrees from each other. They are in time phase because both of them are multiplied by J anyway, and related like in the plane EM wave with E theta by H phi equal to eta, which, and recall that eta is the intrinsic impedance of the medium that surrounds the current element. So this is called a spherical TEM wave, and it's propagating outward from a point source at the origin of a spherical coordinate system along the radius from that point. That is radially propagating outward. So the fields will decay as 1 by r from the dipole, and therefore they satisfy what we call the Sommerfeld radiation condition, where we say that all fields, that is, all field solutions from the Maxwell's equations, must not be propagating any faster or decaying any faster than 1 over r as r goes to infinity. And they must be radiating outward, not coming backward from the source. So since the far field criterion is that Kr be much larger than unity, then this can be seen to be equivalent to requiring that r be much greater than lambda by twice pi, where this is just r is much greater than 1 by k, so you will just get lambda by twice pi, or in other words, we can always assume that pi is approximately 3, and therefore we say that r must be approximately much larger than lambda by 6, okay? And considering h phi, the near and the far field components are equal at r0, such that 1 over k r naught is equal to 1 over k r naught all squared. And we see that the depth boundary between the far zone and the near zone will be for the case where r naught is just lambda by twice pi, which is just lambda by 6. So we also have what we call a magnetic dipole, where we can use a current loop instead. So we consider a circular filamentary current loop of radius b lying in the xy plane and centered at the origin of a Cartesian coordinate system, as we have shown here. So our current element is, of course, that, okay, circular value. We are going to take a small element of length of path along the circular path there at an angle of an angle d phi subtended at the center of the current element. Remember that phi is measured along from the positive x towards that is counterclockwise, if you like, while theta is measured from the positive z and is measured clockwise down towards the xy plane. Now, what you'll notice in this particular case, we have two sets of coordinates. We have a coordinate system that is centered at the field point. This we shall give it as PR prime, PR, theta, and phi. So this is as measured from the center of the current loop. And two, we have a coordinate system that is centered around the current element. And this will be given by phi prime, okay, and r prime and c prime, and whatever, theta prime here for this particular case. And therefore, we look at this following. Now, the radial line connecting the current element, dl, idl here, okay, to the position vector of the field point is given as psi, okay? It's at an angle psi, that is above the xy plane, but it's at an angle phi prime from the x-axis, okay? And has a width of d phi prime. So we have several values to deal with. R prime itself is the distance or the position vector of the field point with reference to the source, that is to the current element. And therefore, we have those things to worry about. So from the geometry, we note that the psi is the angle between the position vector r prime or r of the field point and the position vector b of the current element, because the current element is b away from the center of the current loop, okay? While r at the field point is r, a vector r away from the same origin of the coordinate system. So we'll assume that the current carries a constant amplitude sinusoidal current of the form I of t equal to I cos omega t. This will be constantly distributed about the current loop as long as we assume that B is going to be much smaller than the wavelength of the signal or the current signal flowing around the loop. So the current loop therefore represents a magnetic dipole with a magnetic dipole moment given by m given by z cap multiplied by pi r squared, multiplied by I, and multiplied by z cap m from the Biot-Savart law. So we have at the field point, therefore, that A is going to be given by mu multiplied by the current I and over 4 pi, and the integral over the current loop, that is C, the integration path is around the current loop, and it's a closed integral of the exponent of minus jk r prime over r prime and multiplied by the length of the current element. So since r prime is a function of the location of d prime on the current loop, this integral will be very difficult to evaluate. But what we can do is that when the loop is small, that is when b is much smaller than lambda and r prime is much larger than b prime, that is the field element or the field point is much farther away from the current element than the radius, than that radius of the loop, then the phase factor can be expanded in the following form. So this is what we have done. The exponent of minus jk r prime can be written as the exponent of minus jk multiplied by r prime minus r. Okay, and because of this negative value we have here, when we put it in here, it is going to become plus jkr. And since this is not appearing this here, we subtract it out again. So we have it as the exponent of minus jk of r prime minus r minus jkr. This is to remove the factor that we have added there. And therefore, we can write this as the exponent of minus jkr multiplied by the exponent of minus jk and into r prime minus r. And therefore, if the field point is very far away, then r prime minus r is going to be very, very small. Okay, it will be a small quantity. And therefore, we can expand this particular component or this factor in a Taylor or in a Maclaurin series expansion. So we'll have the exponent of minus jkr into 1 minus jk into r prime minus r minus jk r prime minus r all squared and divided by twice factorial and minus so forth and so forth as we go on. And in the end, we can just take the first two linear terms and we get just the exponent of minus jkr into 1 plus jkr minus jk prime r prime. Now, and therefore A can simply be given as the mu I over 4 pi, the exponent of minus jkr into 1 plus jkr times the integral of the dl by r prime minus jk and the integral of dl prime. And what we notice, the integral over the closed surface, this is going to go to 0. So we can say that the second term integrates to 0, just like you have seen in Kirchhoff's circuit laws or voltage laws, that the voltage drop around a loop is going to be equal to 0. That's the same kind of thing. We are starting from the first point, the end point and the start point are the same. So that one just goes to 0. So, and A will therefore be given by that integral there. Okay? So because of the axiosymmetry of the magnetic dipole, the magnetic field intensity will be independent of phi. And therefore, the field point can therefore be chosen as lying in any of the y of the planes, and we choose the yz plane or in the plane where phi is equal to pi by 2 with no loss of generality as shown below. That is, we could choose any plane, okay, any yz plane along that to do our calculations. But for convenience, we are going to use the r, theta, and pi by 2 at that point. So this simplifies the geometry for the analysis. And what we can see is that for this current element we have here, we have a similar current element there, but the currents are facing in opposite directions, and therefore at their contribution to the vector potential at this point, they are going to be in opposite direction in one of the you know, in one of the x direction, in the whatever, in the z direction, of course, we'll have an addition, while in the x direction, there will be a cancellation, so to speak, of the fields. So we can say that we know that the unit vectors phi prime and phi at the current element and the field point will be different, with specifically with phi, that is phi cap at the field element pointing in the minus x direction. And this we can see in this point. Now remember, x is pointing out, but if we look at this phi at this point here, it will be going into, okay, remember that the x is pointing out, so the phi will be pointing into the screen, and therefore it will be in the minus x direction at that point. But phi prime at this point is pointing in a different direction as that. So the element of path is therefore going to be given by the d of L prime equal to the minus x cap sine phi prime plus y cos phi, and multiplied by the angle or the arc length of that is subtended at the circular point. That is b multiplied by the d phi, the angle subtended at the center of the current loop. Remember, from your theory, it's usually the arc length is going to be given by the radius of the circle multiplied by the element of angle subtended that arc subtends at the center of the circle. So for every current element I multiplied by d L prime contributing to the magnetic vector potential at the field point P, there will be another that is diametrically opposite from it, contributing a y component in the opposite direction. And thus, all the y components will cancel at the field point, while the x components will add, and therefore A will therefore entirely be in the minus x direction at the field point. And hence, A can be given as the minus x cap mu I by 4 pi into 1 plus j k r exponent of minus j k r integral from 0 to twice pi, that is around the full circle, and b sine phi over r prime d phi prime. And remember, we say that the minus of x pi, x cap is of course the same as the phi, the direction of the phi cap, and we can write that one simply as that value there, from minus pi by 2 to pi by 2, for that using the whatever the circumferential or the axiosymmetry of the statement, problem statement. And from that geometry, we can now get what r prime is going to be given by. And we use the cosine rule, or the rule of cosines, and we can write that r prime is going to be given by the r squared plus b squared minus twice br and multiplied by the cosine of phi. I don't know whether we could go back a little bit and show this, that what we are talking about. Remember, the triangle we are interested in is that triangle there. And it has the angle at this point here, that is between B and R prime. We have that angle which is opposite the interest, the length of interest is psi. We called it psi there, that angle, and that is the position vector of the field point. And therefore, by the cosine rule, it's always that r prime squared can be obtained from the r squared plus the b squared and minus twice the b multiplied by the r and less the cosine of the angle opposite the angle at the distance we are interested in. So that's what we have here. That is the sine rule. And we can get the r out, factor it out. That is, we can factor this out because of the simple things we talked about. We say that if r prime was much larger than b, and therefore we expect that r is also going to be much larger than b, and therefore we can always reduce this value, that is b by r squared is going all squared is going to be very, very small, okay? And therefore in relation to unity, and we can let it fall out. And therefore, all we are left with is r into 1 minus twice b over r and the cosine of psi. And therefore, this can be expanded in a binomial series, and we get it a binomial expansion, and we get a value of r into 1 minus b by r cosine of psi. And thus, if we take the reciprocal, because we are interested in the reciprocal in our integral, we can see that that is going to be given by 1 over r into 1 plus b by r cosine of psi. Again, we have used binomial expansion of this, the reciprocal of 1 minus b by r cosine of psi. So we note that r cosine of psi is, of course, the projection of the radius vector of the distance, or that is the radius vector, or the position vector of the field point, okay, connecting to the origin of the current element. That is, r, the r we have with the distance of the field point will be projected onto the radius vector b of the current element. And this is then going to be the same as the projection of the line to the same vector. That is, I can go back again. Sorry for this. What we are saying is that we can take this, that value is going to be the projection of this vector here along the radius vector. And this can also be the projection of that vector, that distance OP, okay, from the center to that point, directed, okay, projected onto the radius as well. Okay, so why are we doing this? The reason why is because we want to describe or to get a fix on what pi is going to be, or psi is going to be. So that's what it means, that r cosine of psi is going to be the same as the OP, the cosine of pi by 2 minus psi phi prime, and this is the same as OP multiplied by sine phi. And therefore, but if you look at the OP is, of course, r cos pi by 2 minus theta, and therefore that is going to be given by r sine theta. And therefore, we can replace OP by this r sine theta into that expression, and we'll get a value that cosine of phi is just going to be given by the sine of phi theta and multiplied by the sine of phi. So we'll use these values, therefore, in our integral, and we place them there, as we have seen there, as sine theta sine phi and multiplied by b sine phi d phi. And therefore, the first term, that is this first term here, will integrate to 0, but the second term will evaluate to a value that phi cap of mu I b squared by 4 r squared multiplied by 1 plus jkr sine theta and the cosine of minus jkr. Or in other words, we can always multiply. We can multiply this top by pi and divide down by pi, and therefore we get this is the area of the current loop, and we are multiplying the current by the area of the current loop. Remember that the area of the current multiplied by the area of the loop is always what we call the dipole, the magnetic dipole M that we obtained before. And therefore, we'll get this given as the A equal to phi cap mu multiplied by the magnetic dipole moment divided by 4 pi r squared into 1 plus jkr, the sine theta and the cosine of minus jkr. So that's the magnetic vector potential at the field point. And therefore, once we have this, the rest we can do is to now start getting the value of H from the curl of A. And this gives us the following, that the H is going to be 1 by mu, the curl of A, and we evaluate that value. And what we get is that we now get a radial component HR given by that value there. Remember that eta is, of course, the intrinsic impedance of the surrounding medium. The K is, of course, the propagation factor K, that we are the 2 pi by pi, by the 2 pi by lambda. And we see the twice cosine here for the HR, and that value the exponent of JKR. If for those of us who have been following, we can remember that we had a similar expression, but for the electric dipole, in which the radio component of the electric field was given by a similar kind of function. That is, we can ignore this beginning term here, and we just look at the twice cos theta multiplying that function there is the same as before. And h theta, we have a j omega mu m of that, and the sign of that value. And again, if we were to look at that spatial factor there, okay, the spatial factor there is the same as for the E theta we obtained for the electric dipole moment, the electric dipole. So the electric field intensity is of course given from the Ampere circuit law as 1 by j omega epsilon, the curl of H. And what we see is that we just have only one component, which is E phi. And again, I'll draw your attention to the expression of H phi in the electric dipole. It had a similar kind of variation. Okay, so we can say the following there. We note that the field components of the horizontal magnetic dipole, horizontal in the sense that we have defined our current element to lie in the xy plane, which is the horizontal plane in our connotation, and therefore are residual of the components of a vertical electric dipole. That is, if we have a dipole, an electric dipole oriented in the z direction, and a magnetic dipole oriented in the xy plane or lying in the xy plane, the components of one antenna will be the components of the other, just by when we manipulate only the multiplying factors. And the multiplying factors are, of course, these values that we have here. Okay. So if we were to say that E of E and H of E are the electric and magnetic field intensities for the vertical Hertzian dipole, and EM and HM are those correspond from the horizontal magnetic dipole, then as long as we have that the current, okay, the current moment, that is current multiplied by length, is equal to JK multiplied by the magnetic dipole, then we can always obtain the E of E from multiplying the eta, okay, multiplied by the horizontal or the magnetic field intensity of the magnetic dipole. And the electric or the magnetic field intensity for the electric dipole is obtained as the negative of the ratio of the magnetic dipole electric field intensity divided by the intrinsic impedance. That's what we call as duality. That is the duals of each other. Okay. So the radiating or the far field components for the magnetic dipole are therefore going to be given by E of phi, and we have H theta given by that expression, which can be reduced in terms of M and pi. And then what we do is that when we take, the E phi divided by H theta, what we'll get a negative value of the intrinsic impedance, so to speak. So below are then the E plane and the H plane patterns for the elemental electric dipole. The E plane is the plane containing the electric field, and the H plane is the pattern of containing the plane containing the H field. And therefore, for the E plane, that is the Z direction, we'll have, that is, the E theta varies or is distributed in space. It's as a circular value. It has constant amplitude, but it goes round like a circle. It's like we have just cut a cross section along that. It's called the phi y z plane, and we have two of them. And if you can try to contort your head a little bit, you'll see that this is called a figure 8, okay? A figure 8 kind of pattern. Now, if you look straight down on top, that is, you are looking at the horizontal plane, then we'll see the H5, and the H5 will be describing a circle. But remember, along the Z-axis, the E field is going to be 0. And therefore, if we are to look down on that point, and we are looking down on this field here in 3D, this will appear as a donut. That is a donut shape, not with a big hole of the donut, but with a small hole there of the where the electric field is going to be null. That is going to be 0, because as just like before, the tangential component of the electric field intensity along a conducting plane must vanish, and therefore there will be nothing here, and this will be called a null position for the electric field. So we note therefore that E theta for the vertical electric dipole and E phi of the horizontal magnetic dipole have the same spatial distribution or pattern functions. 2, they are both in spatial and time quadrature phase, and therefore we can always use a vertical electric dipole and a horizontal magnetic dipole centered at the vertical electric dipole together in space, and will create an antenna that will radiate elliptically or circularly polarized waves in the far field. Remember from last semester, we said that the polarization of the fields or the waves is the position or the time evolution of the electric, or the orientation of the electric vector, electric field intensity vector in space, okay, at a given time, okay, at a given position in space. And therefore, since we have one in the horizontal direction and the other in the vertical direction, we can expect that we'll have something like, you know, if they are, since they are in different time, they have different time phase, then we can get a circulation. So it will be elliptic if one of them has a higher magnitude than the other, or circular if we arrange that both of them have the same value or the same magnitude of electric field. So that brings us to the end of that particular section. And now I'm open to any questions that you might have. So any question then? So you notice that many of the fields computations in magnetic, in whatever antenna theory, they are very involved, and therefore usually when we test your understanding, either you'll be given the solution and then you work from the solution, or we can just confine ourselves to the elemental elements, that is the Hertzian dipole and the magnetic dipole antennas, because these ones are the only ones that render themselves to analytical computation easily. The rest we shall see, just as the same way you have dealt with Fourier series in mathematics, we shall see that any antenna of any length can be considered to be very many, very many small elemental antennas. Then we can just add their contributions at the field point. And this will be important when we start talking about the arrays, the antenna arrays. So any question before I keep on babbling? So silence means there is no question. So I'll give you a 5-minute break. We'll meet at 8 minutes by the hour and continue with something else then. So we'll continue now from where we left. And you can tell me whether you can see that document. Now I'm showing a document called thin linear antennas.
Yes, we can see it.
Okay, fine. So we'll talk about thin linear antennas, but by linear we are saying they are just straight wires. But now the lengths of these wires are no longer small, like the Hertzian dipole, when compared to the wavelength, and therefore we can expect there will be a slight variation in the current distributed over the length of the antenna. Now, we can say that most practical antennas have lengths that are of the same order of magnitude as the wavelength of the signal operating on them. And we'll consider a thin center-fed linear antenna of a half length L that is comparable to the wavelength. By that, we are saying we have a length of 2L, but we'll be feeding that antenna, or that line will be fed at the center. That is, we'll make the center become the origin of the coordinate system. So this will be called a linear dipole antenna. So this is what it looks like. So we have put a thin gap, okay, in the length that is 2L. That length is 2L, but we have put a thin gap there, and we are putting our generator there to feed one arm and the other arm. Okay, this is an antenna that you are all familiar with because it's everywhere around the world, around the country or even the city, and it's what you call a dipole antenna. Of course, some of them you'll see in a different variation, especially the TV antenna. You will find that this length has been folded on itself. So we have like a loop, okay, a long thin loop, and we call it a folded dipole antenna. We shall see why the folding is important for this particular kind of antennas. So we'll assume the wire is infinitesimally thin. That is, it has almost zero radius, okay? And the wire is carrying a sinusoidally distributed current, IZ, as shown below. That is, the current must, of course, go to zero at the ends because the ends are open-circuited. But we are assuming that the distribution is almost sinusoidal along that current, okay? And also the other arm itself. And it has a maximum value of Im, or that is the amplitude of the current is Im in the Z direction. Then we are going to consider a small current element of length dl, okay, a distance z from the origin or from the center feed or the feed point, and a field point that is a distance r prime from that current element and r from the origin, and we'll assume that r and r prime are very large compared to the length of the antenna itself. That is, the field point is very far away. So the current distribution is therefore going to be that of a standing wave over the dipole. And because of the center feed scheme used to excite the antenna, the current distribution must be symmetrical about the feed point. So we can therefore express I of z as I of z equal to the Im sine k L minus z, k into L minus z, for z greater than 0, and Im equal to the sine of k L plus z for z less than 0. That is below the feeding point and above the feeding point. And we find that at the ends of the wire, of course, the current will be appropriately described by those equations, because at z equal to minus L, we have 0, and at z equal to L, we have 0 on the other side. And therefore, the current distribution is properly described by that function there. Remember, we have assumed, okay, we have assumed the current distribution on that wire. It's not that we are saying that it's going to be sine k L minus Z, but we are assuming that that's what it is. Then we'll compute and see whether it agrees with the patterns of the way the antenna should be working physically. And this is what I alluded to in the first place when we say that most of the time the distribution, the current distribution need not be very accurate. It only needs to be just slightly, reasonably, a reasonable approximation. So, since we are often interested in the radiating fields, we are now not going to bother about the Fresnel zone kind of fields. We just deal with the Fraunhofer fields alone. And therefore, in the analysis, we'll consider only the radiating fields. And remember that the radiating fields are those that are varying not than 1 by R from the dipole element. R prime given by this E theta given by eta multiplied by dH phi equal to J Iz dz over 4 pi eta multiplied by K sine theta exponent of minus JK R prime by R prime. Remember, this is a solution for the electric dipole that we already saw before, where dz has replaced the length L we had before, because we had already said that our length L was much smaller than the wavelength for the electric dipole or the Hertzian dipole. And now we are saying that L now is now comparable to the wavelength, but we are looking at the current element of a length dz along the line. Okay, so that's the electric dipole we are talking about for this particular case. Now, if the field point is a distance r that is much larger than the length of the antenna, that is L, from the field point, then in the phase factor, we can make the following approximation, that the R prime, okay, which we can show here, R prime can be given by the cosine rule, or that is the rule of cosines, and we say that this theta is the angle opposite that. The same thing we can be said is that when these ones are very large and that very small, then it means that at the field point, these two will almost be parallel. Not parallel, but they'll almost be parallel as far as we are concerned, okay, at the field point, when these are very, very large, so to speak. So the thetas are going to be the same. Even that will be represented by a value theta as well. Therefore, we can see that when we do that with we take the binomial expressions or the expansion, we shall see that R prime is just going to be given by R minus Z cos theta. So, and in the denominator, we are going to assume that since R is very far, that is, the field point is very far, then those two are approximately equal, and therefore we can write that delta R is approximately R minus R prime equal to 0 will suffice. The reason why we don't assume the same value for the exponent, that is the exponent in the propagation factor, is because K can be large, and therefore the electric length can be large as well. And therefore we can't make those kind of assumptions as we make in the magnitudes themselves in the denominator. And therefore, the element or the contribution of that current element IDZ to the field at the field point, dE theta, is going to be given approximately by J multiplied by that value eta K sine theta multiplied by that whatever propagation factor and multiplied by the phase factor. So the total electric field intensity at the field point will then be the superposition of the contributions from all the current elements that make up the dipole. And thus, we can write that as E theta equal to J eta K by 4 pi sine theta exponent of minus J K R by R, and integrating from minus L to L of Iz, the exponent of JKZ cos theta dz. Now, we can see that we can replace the value of I by its distribution, which we saw was Im multiplied by the sine of K into L minus the modulus of Z for both L and Z. Okay? And therefore, what we have here is therefore that equation there. What we can note is that this will be an even function, okay? While that will be an odd function, so to speak. So we consider the integrand in the following form. That is that sine K L minus Z modulus exponent of JKZ, we can replace this one by its trigonometric function as cosine of JKZ cos theta plus J sine theta, sine KZ cos theta as follows. So we'll have sine K into L minus modulus of Z multiplied by the cosine of KZ cos theta plus J sine KZ cos theta. And we note that for the component integrands, you see that the multiplication of sine K L minus the modulus of Z sine KZ is going to be an odd function of Z, and therefore when we integrate it between two symmetrical integration limits, it will vanish, it becomes 0. The reason why is because this is odd and that is even, and here we have two even functions, and therefore when we integrate these, it will have a non-zero value, and therefore only this component will contribute to the integral that we have between minus L and L, but that one will integrate to 0. And thus, E theta is going to be given by that expression there, and we can get that value as the J60 multiplied by Im exponent of minus J K R by R and multiplied by F of theta. Why we are using this F of theta is because we are multiplying that value there as K sine theta, multiplying the sine K L minus Z of cos KZ cos theta dz, and we are calling it an angular or an angle factor. Okay? So this is the integral. We can show how to integrate this in a few minutes, but for now, let's just stop at that level. Remember, this 60 is because eta is 120 pi for free space, and twice pi will therefore give us 60, and the k, of course, will cancel out. So we evaluate the f of theta by integrating by parts. So the first thing we do is to let u to be the sine of k of L minus Z, and therefore we can get a value of du as the minus of k cos theta and multiplied by L minus Z, and dv to be given by the cosine of kz cos theta dz, or we can get a value of v equal to sine of kz cos theta by k cos theta. And thus we'll integrate that from 0 to L. Because we are dealing with a sine or with an even function, we can always integrate on only one arm and multiply by 2, and therefore we have that value there. And once we put those things in, all we'll get is that we'll just find that that will integrate to 0 because of these values here. This is going to go to 0. KL is going to be 0 there, and this one sine k of L minus Z is going to be equal to 0, and if we put Z equal to 0, that will be 0, and sine 0 is 0, so that one will equal to 0 as well. So we are just left with only this one component remaining, and therefore we have it down here as the integral of 1 over cosine 0 to L, that cosine value. And we now let u to be given by cos k L minus Z, and du therefore gives us a value of k sine k into L minus Z, and the dv equal to that. Or in other words, we can write that v given by the minus of cos kz cos theta k cos theta. And thus, the integral that we had before will be given in that form. That is the first part, and the second part there. Or in other words, that is, if you look at this integral here, and that integral there are the same, only for the scaling factor 1 by cos theta squared, which we can, therefore, we can take this one to the other side of the equation, and we get the following, that 1 minus 1 over cos squared theta integral from 0 to n of that sine theta is equal to the minus of that. And therefore, all we need to do is to divide through and we get our integral of the function. Or in other words, that is going to be given by the cosine of kl cos theta minus cos kl over k sine theta squared, where we are using the 1 minus cos theta squared as the sine squared of theta. And thus, you can see that the angle factor, or it's called the element or the antenna factor f theta, is going to be given by k sine theta, the integral of that equation there, and we get a value of cos kl cos theta minus cos kl over sine theta. That is important to hold on to. So the function f of theta modulus, that is the magnitude of f of theta, is usually called the E-plane pattern function of the dipole. And the electric field intensity at the field point will therefore be given by the J60 multiplied by the current magnitude Im multiplied by the propagation factor exponent minus JKR by R, and the cosine of KL cos theta minus cos KL by sine theta, which is the E-plane pattern function. And for convenience and of the interpretation, then E theta will often be expressed in the form that E theta is going to be given by a magnitude factor multiplied by an angle factor that is characteristic of the antenna, and the pattern, the element pattern, that is the E-plane pattern function, and multiplied by the phase propagation factor. So the first term is called the amplitude factor. The second term is called the element pattern function. That is, if we had a small point radiator, the factor, okay, the pattern factor will just be sine theta. If you remember, when we looked at the Hertzian dipole, we were multiplying the magnitude with only a value sine theta. And therefore, all we are saying is that this value here is coming in because we have very many dipoles along that line. That our dipole has very many small elemental dipoles. And therefore, this we shall call it later as the array factor when we look at array antenna arrays. So the third pattern, of course, is the array pattern of the E-plane pattern function. And the first term is, of course, the usual propagation or the phase propagation factor for the plane wave or for the propagating waves. So the most important dipole that you'll get in use practically is what we call the half-wave dipole. That is, the half length L is equal to quarter lambda. And if you recall from last semester, we said anything that is quarter lambda will have, if you were to look at the input impedance of either an open circuited or a short circuited element or transmission line that is quarter lambda long, it will appear to be resonant. That is, it will go to Z0 squared over the ZL terminating that value. That is an impedance transformer. And it's because of the resonance of that value. Okay? Because the tangent of pi by 2 is always going to be equal to infinity, so to speak. So we note that KL is therefore going to be given by twice pi divided by lambda and multiplied by lambda by 2, and therefore we have a value of pi by 2. And therefore, our E-plane pattern function is going to be reduced to, remember that cosine of KL, and we put the KL there as pi by 2 will be now cosine of pi will fall out because cosine pi is pi by 2 is 0. And the only one we are left with is the cosine of the sine of something multiplied by the cosine there. That is, this is what we are saying, the pattern factor. Oh yeah, I think this is what we are dealing with. That is, we replace KL by pi by 2 in this pattern factor. So the sine of pi by 2 is of course unity. The cosine of pi by 2 is 0. And the cosine of that is going to be the cosine of pi by 2 multiplied by cos theta. Okay? I hope that one is now clear. So this is what we have. We have just the sine theta. The sine theta, of course, is not going to go because we are not replacing the theta. It's just the KL that is being replaced by pi by 2. So we note that as theta varies from 0 to pi, then we can see that the pattern, the magnitude of f theta will have a maximum value of unity, and it will occur at the positions where theta is equal to pi by 2 and will be 0 when theta is equal to 0 and or it's equal to pi. That is along the dipole. So the electric field intensity in the far field zone is therefore going to be given by the value of j theta. J is 60 Im, the exponent of minus j k r by r, the cosine of pi by 2 cos theta over sine theta, and the h phi will be given by e theta divided by the intrinsic impedance of the medium, and we just get that value there. And therefore, the time varying Poynting vector is therefore going to be given by the half the real part of E cross H star. And what we get is that we are going to get 1 over 2, the real part of theta cap cross phi cap multiplied by E theta and multiplied by H phi. And what we notice is that theta cap cross phi cap is in the radial direction. And therefore, we get a value of about 15 Im squared by pi r squared, the cosine of pi by 2 cos theta by sine theta all squared. That is the pattern function squared. The magnitude of the pattern function squared and multiplied by that value of the amplitude. That is the current itself. So that is the average, the time average Poynting vector, and we see that it's entirely radial. That is, it's radiating away from, the power is flowing away from the origin of, that is at the dipole, and radiating radially outwards. So the total time average power that is radiating in the r direction will therefore be given by the PR equal to the integral over the closed surface that is enclosing the antenna itself, and it's therefore multiplying, we integrate the Poynting vector, average Poynting vector over that radius, so to speak. And we know that the radius of a sphere has a unit vector is directed in the direction of the radius. That is the radial vector. And this is equal to that value there, integrating that particular value there. What we see is that the r squared here will remove the r squared there. Remember that r squared sine theta, d theta d phi, this is the element of area on the sphere, on a sphere, okay? On a spherical element of area, that is ds there. And what we get is that we'll have a value of 30 Im squared, the integral from 0 to pi, because if you look at this integral, it does not vary with phi. It's not a function of phi, it's only a function of theta, and therefore we can integrate from 0 to 2 pi on the horizontal axis. So we'll get a 2 pi multiplying that, and therefore we'll get something like 30 and Im squared for that particular part, and we fail at that, and therefore we are left with the cosine of pi by 2 cos theta by sine theta d theta, which is going to be given by 30 Im squared p multiplied of theta. This integral is usually a little bit difficult to integrate, and we shall see how we can deal with it. So to evaluate p theta, we have to express it in the form that is the integral from 0 to pi equal to a half of 1 plus cos pi cos theta over sine theta. All we have done is that we have replaced this value. We know that the cosine of twice theta is equal to the cosine of theta minus the sine of theta. Or in terms of cos theta, we can always write it as the cosine of 2 theta is equal to twice the cosine of theta squared minus unity. So therefore, we can get the value of the cosine squared of pi by 2 cos theta, where we are now using that, and therefore we get that it's going to be given by a half of 1 plus the cosine of pi cos theta. And then we are dividing it by sine theta there to get the d theta to get the integral. So that's the only thing we have done there. So we'll make the change of integration variable by letting u equal to cos theta, so that d theta is the same as the minus of du and divided by the sine theta. And we note that whenever theta is equal to 0, u will be unity, and when goes to when theta goes to pi, the u is going to be the minus of 1, or that is minus 1. And therefore, we can integrate our function as p of u integrated over the minus of 1 by 2 integral from 1 to minus 1, 1 plus cos pi u over sine squared theta. And this can be changed into a cosine function by using the trigonometry identity that cosine squared theta plus the sine squared theta is equal to unity. We can change that sine squared theta to cosine squared as 1 minus cos squared theta. And remember that cos theta was expressed as u, therefore this will be u squared. And therefore we have this value. We have removed the negative sign by interchanging the integration limits from the minus 1, from 1 to minus 1 to minus 1 to 1. And therefore we have a half of the integral from minus 1 to 1, of 1 plus cosine of pi u over 1 minus u squared and du. Now, or in other words, we can use the partial fraction expansion of the 1 minus u, and we'll get a value of 1 plus u plus 1 over 1 minus u, and we are multiplying that by the following values there. And therefore, we have two functions. That is, we have a half coming from this expansion, and the half that was multiplying. So we have a quarter now of the first term and the second term. So we consider the first term first and call it p plus of u. That is the integral with respect to 1 plus u at the bottom. And we can make now another change of integration variable by letting that v be expressed as v equal to 1 plus u multiplied by pi. And therefore it means that pi u is going to be v minus pi. And therefore du is just going to be dv divided by pi. And we make the following observation, that when u is equal to minus 1, v must be 0. And when v is equal to u is equal to unity, v must be twice pi. And therefore, we can integrate the first term in that form, and we get a value of the cosine, that is the integral from 0 to twice pi of 1 plus cos v minus pi. And of course, we can expand that, okay, into the usual value, that is cos pi cos v plus sin pi sin v. And you see that the signs will fall out, and we are just left with the minus of cos v. And therefore, this is the integral that we'll be trying to solve. So the second term, we make the same substitution, but we use a different variable t, and we'll make it as t equal to pi 1 minus u, and therefore we can make the following values, and we see the values as they appear there. And thus, we see a p minus of theta being given by that value divided by that over t. Now, what we have in ought to see is that these expressions, they look similar or is the same as the expression where we were using V. And therefore, we can say that since V and T are dummy variables, the integrals should have the same value, okay, once we evaluate them. And therefore, we only need to evaluate one of them, and then we'll add them together. So we can therefore write that the integral of that cosine of pi by cos theta by sine theta is equal to d theta is equal to 1 over 2 integral from 0 to twice pi 1 minus cos theta, cos v over v, and multiplied by dv. Remember, we are using only one of them and multiplying it by 2 because they were in addition, and therefore all we can do is to express the cosine of v in its Euler form, that is exponent of jv plus exponent of minus jv divided by 2. So this is what we have done here. So we have 1 over v minus 1 over 2v into the exponent of jv plus exponent of minus jv. And then all we are going to do is to expand this one in a Maclaurin series to get the expansion for the cosine, and we get a value of 1 over minus v squared by 2 factorial plus v power 4 by 4 factorial minus v power 6 by 6 factorial plus and so forth. You know the expansion of the cosine in the Maclaurin series, or the series form of the power series expansion of the cosine of v. And therefore, all we do is to multiply through. We see that the first one, the first term will fall out, but the second term will be multiplied by divided by this, and we get the following form there. And now, this series, once we have integrated, we'll integrate this term by term, and therefore we'll get v squared by 2 multiplied by 2 factorial, v power 4 multiplied by 4 multiplied by 4 factorial, and v power 6 times 6 factorial, we'll get v power 8 by 8 multiplied by 8 factorial and so forth. And for v equal to pi by twice pi. That is when v is at the top here, is what we are just interested in. Because at the bottom, it's just going to be 0, so we'll be subtracting 0. So we are just going to deal with v when v is just twice pi for that expression. So that integral will be equal to that expression there. So the series converges very, very slowly, however, which is an unfortunate thing. But if we use 8 terms, we can write the sum P8 of theta, it integrates to about 1.218. What I can ask you to do is that when you go back home, or when you start dealing with when you are unwinding for the weekend, you can try to use the 8 terms here, that is, continue expanding this to 8. And what you'll get is that once you put the values of twice pi in there, you are going to get these values. You'll get a value of 1.218. Okay? And thus, the PR, or the power propagating outward from the dipole, is going to be given by 30 Im squared P theta, which is approximately, using that, will be 36.54 Im squared. So the equivalent resistance, RR, that would dissipate the same power, okay? That is, if we were to take a current of I, of amplitude Im, and pass it through a resistor, how much will that resistor be, or how big will that resistor have to be for it to dissipate the same amount of power as PR that we have? And therefore, since power is given by a half Im squared multiplied by R, okay, we can get that equivalent resistance RR as twice PR divided by the amplitude squared. And this is approximately 73.1 ohms. And therefore, for the half-wave dipole, the RR, which is an equivalence resistance, will be called the radiation resistance, and therefore it has a value of 73.1 ohm. If you have been keen to look at the back of your TV, you'll find that the antenna connector is usually indicated as 75 ohms. Okay, so it's by design in this convention or the standard, that 75 ohms has been taken as the industrial standard, and we can see that the reflection coefficient, when you connect the antenna to that, is going to be very, very small, so to speak. If you use a 75 ohm transmission line, the reflection coefficient is going to be small, really. So RR is really not a resistor, a real practical resistor, but a fictitious resistance that describes how power is radiated by the antenna. And therefore we call it the radiation resistance of the antenna. So the radiation resistance of an antenna is an important performance parameter in the antenna design. So if losses in the dipole wire are negligible, the half-wave dipole has a slightly inductive input impedance with a real part of 73.1 ohm. The inductiveness is because of the end effects at the open circuits. It's more like you are adding a capacitance to it, and therefore you must have an inductive reactance to that quarter wave or to that length of wire for it to resonate at the quarter lambda length. So the inductive reactance can be resonated out by making the dipole slightly shorter than lambda by 4, which is usually done in practice. Usually we use, rather than 0.5 lambda, we use something like 0.498 or 495, okay, as the length to get that inductance off. So an important parameter in antenna analysis is what we call the radiation intensity of the antenna, and it's usually described by the factor K as a function of theta and phi. And it's defined as the time average power per unit solid angle, where a solid angle is the angle subtended by a spherical surface at the center of that sphere. So since a spherical surface of area r squared will subtend a solid angle at the center of the sphere of radius r, then we can see that K, phi of theta, is equal to r squared multiplied by the modulus of the Poynting vector. So, and therefore, PR, or the radiated power, which was given as the closed surface integral of the average Poynting vector over the surface, is equal to the integral, the closed integral over the solid angle of K, phi, theta, phi, and d phi, where the d phi, or the d omega, or the solid angle, element of solid angle, is given as sine theta, d theta, divided by d phi, as is the element of solid angle. And this is usually measured not in radians, but we call them steradians. And therefore, a sphere has a total solid angle of 4 pi. So this is the way we are defining the solid angle. We have the sphere is of radius r, and we are taking a small radius, a small area S, and this area S is subtending an angle at the center, or a conical angle of omega. So that's how the solid angle is defined, more like the angle of an ice cone. So the maximum radiation intensity for the half-wave dipole we saw is when theta is equal to pi by 2, and therefore K max is going to be given by r squared multiplied by the Poynting vector, length of the Poynting vector for theta equal to pi by 2, and we get a value of 15 pi by Im squared. And the directive gain of an antenna, which is given the symbol GD as a function of theta and phi, is defined as the ratio of the radiation intensity in a given direction theta phi to the average radiation intensity, that is, GD of theta phi is given by K, given by theta by phi over K average, where K average is the average intensity or radiation intensity over a whole sphere, assuming that the antenna is radiating power equally in all directions. And therefore, we see that that is going to be given by K, P theta, K of theta phi divided by the radiated power divided by the solid, the total solid. This PR is radiated equally in all directions of us in a sphere, in a spherical direction. And therefore, we get a value of 4 pi K of theta phi over the integral, the total integral of K theta over the solid angle there. And the maximum directive gain of the antenna will be called its directivity, and is therefore the ratio of the maximum radiation intensity to the average radiation intensity, that is GD max. Okay, we are taking the maximum value. The GD itself is a function of phi and theta, but the GD max is now in the direction of maximum radiation, and therefore is going to be given by K max over K average, and we get a value of 4 pi multiplied by K max divided by the total radiated power. Thus, for the half-wave dipole, we have the directivity as 4 pi multiplied by K max over PR, which is 4 pi 15 pi by Im squared over 1 over 36.54 Im squared, and we get a value of 1.64, which is usually given in terms of dB, and we give it as 2.15 dBi. The dBi here means that the reference antenna is an isotropically radiating source, that is a point source. A point source will radiate in all directions equally in a spherical space. And therefore, this value here is given with reference to a point source that will be radiating the same amount of power equally in all directions. So we see that the half-wave dipole is slightly more directive than the whatever the point source. So the half-power beam width of the antenna is defined as the angle between the magnitude, where the magnitude of the E-plane pattern function or the array pattern drops to 1 by root 2 of the maximum value. And since we saw that the F theta is given by the cosine of pi by 2 cos theta by sine theta, we will equate that to unity there, to 1 by root 2 between 0 and theta, to 0 and pi. Then we can see that a numerical or graphical solution will show this to be a value of about 78 degrees. So example, a thin vertical lambda by 4 antenna is excited at its base by a sinusoidal voltage source and is situated over a large grounded conducting plane. Determine A, the radiation pattern of the antenna, B, the radiation resistance of that antenna, and C, the directivity of the antenna. So we show the geometry of this level. We are feeding the antenna, the quarter wave antenna, at the base of it, which is placed over a high conductivity ground plane. And therefore, we can use the virtual images theory and reflect this into the ground plane. And remember that the boundary conditions require that the tangential electric field along the ground plane vanish. So we'll remove the ground plane, then we'll connect our actual radiator there, and we have now the virtual radiator. And for the boundary conditions to be satisfied here, the current must be in the same direction as in the upper one, so that the E will be in opposite directions at the ground plane, so that they cancel out. So once we have done that, okay, that is, once we have it, this is exactly the same problem that we have already solved of the half-wave dipole that we have just been dealing with. So we are going to solve this problem by ignoring that we just have only one half of it. But remember, the only valid field distribution will be that above the ground plane, and therefore it will be half of what the figure 8 we had before. So we had a circular value, but now we have just a value that is only halfway up. So we'll take that and discard the rest. The only reason that we are doing this is because we already know how to solve for the full dipole, and we already have a solution. So to get the monopole or the one pole alone, we can now just use the half, the full dipole, and just take half the solution. So we apply the method of virtual image source to eliminate the grounded conducting plane as shown. And we note that the image antenna is a quarter wave antenna carrying a current flowing in the same direction as the real one to satisfy the boundary conditions on the conducting plane. We therefore recognize this as the the half-wave antenna we have just discussed. However, we just must note that only the radiation field above the ground plane is valid, or in other words, we must only consider theta values between 0 and pi by 2 rather than 0 and pi. So the radiated power is going to be half the original power. We'll get it as 18.27 Im squared. The square is missing. The radiation resistance will be the same, will be half the original one, because now we have 2 PR over Im squared, which is just 36.54. And the K max will be the same as for the half-wave dipole, while the K average is just going to be given by PR over 2 pi. And therefore we see, since the surface, the solid angle we are dealing with is only 2 pi, that is half the spherical solid angle, and therefore we have a directivity of 1.64, which is exactly the same as that for the full dipole itself in terms of directivity. So the monopole, you have seen them, especially in, if you remember the earlier, you used to call them Mulikamuizi or something, the earlier phones, they used to have a small sticking out dipole or antenna, or many of the vehicles, most of the antennas on vehicles are usually just one side of a dipole. So with the ground plane being the body of the vehicle, okay? So that's what you would get for the monopole. So for convenience of analysis, we define an effective length of an antenna, okay? So that we can always relate all our values to that effective length. Now, the effective length LE of theta is defined as the radiated time average. That is the length for which the radiated time average is proportional to it, to L theta. So consider a vertical dipole antenna of half length L carrying a phasor current of Iz. So the far field, electric field intensity, is given by that integral that we have already seen before. Now, we'll define I0 as the current at the feeding point of the antenna, and therefore express E theta in the following form. That is, we'll take an ith naught, then we'll normalize the Iz that is flowing on the line, normalize it to the current at the feed point, and integrate it. And therefore we'll get a value of 30 by R I naught K L E theta, an exponent of minus j K R, where L E theta is therefore defined as this bracketed term there. And that will be called the effective length of an antenna when the antenna is used to transmit the field, that is to transmit the signal. When it's receiving, it will have a different kind of definition, but we shall see they are going to be equivalent. So LE theta is therefore a measure of the effectiveness of the antenna as a radiator of electromagnetic waves. So in many applications, we only need to specify LE of theta at the maximum direction of radiation, which we saw was the theta equal to pi by 2. And thus, LE will be given by LE of pi by 2 and given by that integral there. And therefore, LE will therefore be the length. An equivalent antenna carrying a uniformly distributed current I naught would have to have a far field electric field intensity at theta equal to pi by 2, that is equal to the antenna carrying the actual current, okay, current distribution. So example, determine the effective length of a thin, straight, half-wavelength antenna fed at its center by a sinusoidal source such that the current distribution on the dipole is sinusoidal. And then determine its maximum value. So we assume the current distribution of the same form as we have already done, and we get a value of I naught equal to Im, and therefore we can write that LE theta equal to Bm by sine theta, exponent of that value there. And you recall that we already know how to integrate that, and we got a value of cos pi by 2 cos theta by sine theta there at L equal to pi, KL equal to pi by 2. And LE max is therefore going to be given by that value for theta equals to pi by 2, and therefore we get a value of twice by K alone there. So we can see that this is going to be pi by lambda by pi, and we recall that this will be smaller than lambda by 4. Is it correct? Doesn't sound right. Lambda by pi should be larger than lambda by 4, I would say. So I theta or I0 in the definition for LE theta decreases progressively as L goes towards lambda by 4. And since in this case, Im will not be at the position z equal to 0. And thus, LE of theta is going to be greater than twice L, making the definition useful only for relatively short antennas with maximum current at the feed point. So, the effective length of the antenna when it's receiving is usually defined by the following structure. We are assuming that we have an antenna in space, and there is a plane wave approaching the antenna from that end at an angle theta of incidence. So, we consider a vertical dipole illuminated by a plane wave with an electric field intensity EI in the plane of incidence as shown below. So, for a receiving antenna, the LE of theta will be defined as the open circuit voltage developed at the gap divided by the incident electric field. So VOC is the open circuit voltage induced across the antenna terminals by an incident electric field EI. And the common component of EI that is normal to the antenna will not contribute to this VOC, because EOC will depend on EI, theta, and Ka in a complex way. So from the reciprocity theorem, the effective lengths of an antenna when receiving or when transmitting must be the same. If you recall the reciprocity theorem from last semester, is what we say that the excitation at one point will be the same as the other on the other side when we deal with it. That is, if we have a radiator at the moon and one at the earth, then the field that will measure at the moon from the earth, from the radiator at the earth, must be the same as if that radiator at the earth was transported back to was taken to the moon and you measured its radiation strength at the earth itself. That's what we said about the reciprocity. And if EI is not parallel to the antenna, that is that the EI itself is not polarized parallel to the antenna, then we have a polarization mismatch, and therefore VOC will be given by EI dot the length vector. And VOC will hence be maximum only when EI is parallel to the antenna, and we usually say that the antenna and the radiation, they are now perfectly matched. So we call it a perfect polarization match. And that's why you find that for TV antennas, they are always arranged horizontally because the E field in the picture is the polarization of the signal from the broadcasting house is usually polarized along in the horizontal plane, that is the XY plane, which is parallel to the Earth's surface. Okay, if you look at the police line in the police stations, you'll see similar dipoles, but these are oriented vertically because for police communication, their signals are polarized in the vertical direction to avoid interference with the civilian kind of communication. So that brings us to the end of that particular section. And now I think my time is also up. And in case we have any questions, you can ask them now. And there are guys who keep on asking to be admitted when the class is up. I don't know why. So what's the question about integration being complex? If the integrals are complex, why not just tabulate them from experimental analysis and use that? Of course, in antenna design, we have handbooks. But don't forget, here we are in the academic. The reason why they are done by, the experiment itself must be also validated by theory. Okay? And since we are not training to be technicians, the guys of monkey see, monkey do. We also need to know how to do some of these things, to know where they're coming from, and to know what is what we are the structure is going to be capable of. Today, there are people who can design antennas without even knowing anything about Maxwell's equations, because we have a lot of simulation software such as CST Studio. We have things like FACO, and so forth for antenna design. So really, you don't really need to solve any Maxwell's equations anymore. But you really cannot ask that because we are in a class of engineering science, and we must know how these things come about. Yeah, if you're going to be contributing to the field, of course, you need to know the actual values, because by definition, an engineer is a person who uses knowledge of mathematics and the physical sciences to solve human problems. So I hope that one is good enough for you, Mr. Mutisia. So any other question? So since there are no squeals, then I'll wish you a nice weekend, and let's meet next week then.
Thank you.
Okay, bye.